Hello, everybody. Welcome to the fifth week of this program. From this week up to the last for 12 consecutive weeks, there are two advanced courses. I mean, you can call it courses if you wish. I mean, they're not really very advanced, but some interesting courses, I think. One is given by Ilya. It was given this morning, the first week of it. And the other by me on reproducing kernel Hilbert spaces. From the first week of the program, we have already seen examples of RKHS. First week was Hardy spaces, second Dirichlet space and its variants, and then Bergman space, and then model spaces. Each one of them is an example of RKHS. So in this course, we want to look at these objects from abstract point of view. So, and study their foundation. And then, of course, we pay special attention to specific examples. Indeed, this week and pretty much all of the next week, I will start with the definitions, the original definitions, and then many examples, because with these examples, first we see different versions of RKHS, and second we see how vast they are. I mean, they touch many different subjects of mathematics. For the reference, let me share this page. Do you see it?
Yes.
Okay. That's a book entitled An Introduction to the Theory of RKHS by Vern Paulsen, which is now at the University of Waterloo, and Marina Raghupati at United Services Automobile Association. I think he's in industry. So it's a very good book. It's it has two parts. It covers the basic material, and then the second part, some application in different topics. My goal in this course is to cover at least the first part of it. I mean, those I can tell you, I have a version here in front of me on the other screen from chapter 1. At least up to the end of chapter 6, which are the basics of RKHS. And there are many more interesting chapters in the second part, which is on the application and examples. We will touch that part too, but our main goal is those 6 chapters as much as we can. Then, over the time, we will see how much we can proceed. I suggested 2 more books. Some materials will be covered from those books. When time arrives, I will explain. One is the book of John McCarthy, and the other is my own book on Hardy spaces. But Vern and Marina book is our main reference. Okay. No technical problem, please. Oh my goodness. Try to see this pen I tested this morning. It was working.
Maybe it's because you are in text maybe you have to change the selection.
Who changed my? Did you change it?
No. In fact, at the top of your.
Yeah. Oh, it works now.
Okay.
I think I put the battery upside down inside, so it works now. So very good. Before starting, there are two types of participants in this course. Those have already registered either at Laval University or via ISM, I mean the graduate program ISM. For them, there will be some homework and evaluation and a final exam. I mean, I will discuss further with them in another moment. And those who are there just to participate. If you need a grade, an official grade, please contact me after the course because there are some steps to be taken. If you just want to participate and no grade is needed for a student, that's okay, we go ahead. So if no question, we start the course. RKHS. Reproducing kernel Hilbert space. So the first important word in this is Hilbert space. When we study Hilbert spaces in courses like measure theory or functional analysis, I mean, I assume everybody knows the definition. It's an inner product space such that the norm is complete. So it's a kind of Banach space whose norm satisfies the parallelogram law. It's von Neumann theorem. So after, I mean, doing this, there are some celebrated examples like Liddell LO. So Liddell LO, either defined on N or on Z, is the sequence of vectors which are square summable. Doesn't really, for us, it doesn't really matter if you start from 0 to infinity or from 1 to infinity or from minus infinity to infinity. All versions exist. That's the first Hilbert space, which was used by Hilbert himself. And then at the beginning of 20th century, measure theory by Lebesgue came into surface, and the LP spaces were introduced. LP of mu, the Lebesgue spaces, in particular for p equal to 2, L2 is a Hilbert space. Again, it's a deep theorem. It's not something trivial that L2 of mu is a complete inner product space. So in our terminology, it's a Hilbert space. And that's indeed was one of the main reasons the theory of Lebesgue succeeded. His spaces, LP spaces, are complete. If you read the history of integration theory at the time, there were several other theories, but finally the Lebesgue theory, I mean, won the race. And there are some reasons for that. And one of those is that LP spaces are complete. So we have little L2, we have capital L2, and also some other examples. When you study a little bit more, you have, for example, Hardy spaces that we saw in the first week, and then Dirichlet space and Bergman space. Either we use A2, and in some books they use B22. Both notation exists. All of these are examples of Hilbert spaces, separable Hilbert spaces, and there is a structural theorem which a bit, shaken our understanding. The structural theorem says that if you just consider the Hilbert spaces from abstract point of view, there is just one, I emphasize, just one separable Hilbert space. More explicitly, if we want to apply this theorem here, this means that from a structural theorem, implies that, in a sense, L2 is the same as L2, of mu for a specific mu. For example, we can stay on R, or we can stay on the unit circle to be infinite dimensional, and it's equal to H2, equal to D, equal to A2, and so on. And if the equality bothers you a bit, you can put a tilde over the equality, just to emphasize the fact that we do not look at them as sets. Of course, as sets, they are different, but from the point of view of Hilbert spaces structure, the structure of little L2 is the same as the structure of capital L2, the same as the structure of H2, D, A2. They are all one Hilbert space. So that is why I said knowing this theorem, which is true, of course, it shakens a bit our understanding. So why do we go, if they are the same, which really they are, why do we go for different Hilbert spaces? And there are some justifications for this. Each have their other structures, not just Hilbert structure. They have other structures. For example, in H2D and A2, complex analysis come into picture. In L2 of T and L2 of R, harmonic analysis come into picture, and the interplay between them. There are many other things which are involved. One of them is RKHS, the subject of our course. When we define Hilbert space or Banach space from abstract point of view, we do not pay attention to the nature of elements. We assume there is a set, and there are some operations, addition, scalar multiplication, and they satisfy a set of axioms. For example, commutativity, there is a neutral element, and so on. All of these algebraic properties. So it's really abstract. We don't care what is the element, but they should satisfy some properties. In the definition of RKHS, which we will see momentarily, we do care about the elements. At least there are two properties that we emphasize they should satisfy. First of all, they are functions. So element of RKHS are functions. And second, more importantly, we connect the topology of Hilbert space to these functions by assuming the third property, which says that evaluation functionals are continuous. Let's write this more explicitly. So here is, to give the definition, assume that omega is a set. No further restriction on omega, it doesn't matter what it is. And we can see the capital F of omega and R, or capital F of omega per C. This means that the functions, the set of all functions which defined on omega and are real valued or complex valued. So therefore, you see that we have two sets of or two families of RKHS, real ones and complex ones. In many examples and many theorems, it really doesn't matter we are working on R or on C. The theorem equally holds for both cases. In order not to repeat everything twice, a tradition is to say that F is our scalar field. So it's either equal to R or F like this is either equal to C, one of them, either R or C. And we consider the family F of functions defined on omega and with value in the scalar field F. So that way we can state our general in a more general setting. F of omega and F is surely a vector space. You know how to add functions and multiply by scalars. It's a vector space. And what we want to consider is a subspace of this. So, definition. We assume H, that's the notation we mostly use for an RKHS, is a subset of F, omega, and scalar field F. Up to here, it means that F is a collection of functions. And then we say that H is an reproducing kernel Hilbert space. That's the abbreviation I will use all the time on omega. So this is something I want to highlight. If the following properties holds, if the following hold, three axioms or three properties. First is an algebraic property. Okay. We assume that H is a subspace of FH. Of F omega F. Note that there is no topology involved up to now. When I say subspace, doesn't mean close. I mean, closeness has no meaning here. Subspace, and some books write linear manifold, simply means that it closed with respect to addition and scalar multiplication. That's the meaning of subspace here. The second, now a topology come into picture. Topological property. We assume that H is endowed. Oops, I lost my screen. With a Hilbert space structure. What does it mean? It means that there is an inner product, which I will denote by this notation. And if I want to emphasize we are in H, I will put an H here. It's an inner product, and the corresponding norm, which comes out of this, is complete. So up to here, we have two properties. First one, an algebraic property. The second one is a topological property, and they are somehow isolated. There is no connection between them. The second one is the bridge, is the connection. The third one is the connection between the two. For each x, we assume for each x in the space, the evaluation function we denote it by EX is defined from our vector space to scalar field by this formula. EX of F is defined F of X. That is why it's called the evaluation functional. For sure, it is linear. That is kind of trivial. But absolutely, there is no clue that it has to be bounded or equivalently continuous. And it is not indeed in the general case. The third assumption says that this linear functional is continuous. That's a heavy assumption, which is equivalent to say that it's bounded. Number three is the beginning of RKHS. By putting this assumption, which looks very naive and elementary, but very soon you will see that, oh, it really changes the game, and many interesting things can be proved when we add this property. We start with an example. A very interesting example. You all know the space Cn, that's our H indeed. The way we usually look at Cn, we consider it as vectors of dimension n. Sometimes we write it horizontally. Sometimes we write them vertically, but usually that's the way we think about element of Cn. But let's look a bit differently to Cn. Consider the set omega 1, 2, 3 up to n, a finite set. And instead of saying that z is a vector of dimension n, say that z is a function on omega with its value in C, and at point j, z of j is the same as we had before, the j's components. So in this way, we look at elements of Cn as functions. So in this case, H is precisely equal to the set of all functions defined on omega with, I'm sorry, I mixed between French and English, with its value in C. And omega is this omega that we have, very specific omega. What is our inner product here? The inner product between Z and W, in linear algebra books, it's written as sum j from 1 up to n zj wj bar, which is perfectly fine. But allow me in the light of the function view that I introduced above, write it this way. Instead of z index j, I write z at point j, that's okay, and w at point j bar. So it's a new way to look at this space. It's a Hilbert space. And the evaluations, they are bounded because the formula that you see here, if z is equal to w, the norm of z in h squared is sum j from up to n, absolute value of z j squared. So let's go back here. What is E of x, or if you like, E of j? So fix j in our set. Ej is defined on Cn with its value of inside C. Our f is C. And what does Ej do? Ej, acting on z, is the value of this function z at point j, or zj like this. Therefore, absolute value of Ej of z is equal to absolute value of z at point j, or absolute value of zj, which is less than or equal to the sum k from 1 up to n, absolute value of zk squared, then root square. Because from k equal to 1 up to n, one of these zk is zj. So the sum is bigger, and this is precisely the norm of z in our RKHS. So for each z in the space, which is Cn, absolute value of Ej of z is less than or equal to the norm of z in H. That is precisely what we want. This shows that Ej is continuous on H. And actually, moreover, the inequality that we have above shows that the norm of Ej as a functional on Cn with its value on C, this implies that it's less than or equal to 1. This implies this. In fact, equality holds. Just consider the canonical basis. But this is enough for us. This is enough for us. So I add just in parentheses, actually, equality holds. But I don't need that. This implies that Ej are continuous. I already wrote. So we have our first reproducing kernel Hilbert space. So Cn is an RKHS on what? On omega. Our first example. Many more. As I said, this week, next week, and next week, and probably even the third week, we will see many more examples, because these examples are a foundation of our course. Cn is the most basic one. A bit of generalization of Cn. We saw Cn as a function on omega. such that the norm is defined by this sum. Omega is finite, so there is no convergence issue. We can assume, or we can take any omega, doesn't matter how big omega is. So it's a bit generalization of the previous example. Any set. So no restriction on omega. And we define L2 of omega. What is L2 of omega? Is the set of all functions f defined on omega with values inside f. So we have two versions, either the complex version or the real version. So general setting we say in f, such that not any function, sum x in omega absolute value of f of x squared is finite. If omega is finite, some explanation here is needed. If omega is finite, for example, n elements, we obtain what we had before. Then L2 of omega is the same as Cn that we saw before. If omega is the set of natural numbers, 1, 2, 3, then this becomes an ordinary series that we see in our elementary courses. And it says that the series should be convergent. So in this case, L2 of omega, we simply write L2. Sometimes, in particular, even in our courses, starting from 1, we start from 0, but that's not a huge difference. A slightly variant of the same type, the same omega, is when we consider Z, it's 0 plus minus 1 plus minus 2, and so on. Here, L2 of omega, to distinguish it between this and the previous case, we explicitly write L2 of Z. And our summation here will be sum from minus infinity to plus infinity. So let me write here 3 different cases. Here, sum is from 1 up to n. The second case, sum from 1 to infinity. And the third case, from minus infinity to infinity. These are the cases that we have seen before. This series we have seen before, and we are familiar with them. Maybe some of you haven't seen this before. What happens if omega is not countable? For example, what do we do if omega is equal to r? Then what does this mean? Sum x into r, absolute value of f of x, to f of x squared. So in this case, not just for r, for any omega, countable, finite, or uncountable, it is possible to give a definition which works in all cases. In finite case and in countable case, we end up with what we have seen before, but we need to be very careful in the case omega is not countable, is really big, then some differences exist. Here is a definition. The sum x into omega, something positive, and something positive here is absolute value of fx modulus square. Is defined this way. You calculate absolute value of f of x squared on x over a set f when f is finite and f is a subset of omega. So you consider finite subsets of omega, and when it's finite, the sum x in f mod f squared is well defined. Of course, this quantity depends on capital F. So what we have here is something which depends on f. And now you put supremum here over all f in omega f finite. Indeed, since f in omega f finite is written, I can remove it from here. So that's the definition of that summation. At the end of the day, there is an interesting phenomenon here. You can show that when this quantity is finite, so I leave it as an exercise. Connection between uncountable case and countable case. So exercise for you, if the sum absolute value of f squared x in omega is finite, then there is f, in order not to mix f here with f over there, let me write E. There is a set E in omega, E countable. That is why I choose E instead of F. So it's a countable set such that the sum x in omega, absolute value of f of x, is the same as the sum x in E, absolute value of x squared. And the advantage of the second one, x in E, is that it's countable. You can enumerate elements of E and write this as sum n from 1 to infinity absolute value of fxn squared. It's what we have seen before. That's a simple exercise for you. Usually it's an exercise that we give in measure theory. But you need to be very careful here in the sense that the set E depends on X. Depends on the function that we consider. If we change our function, our set changes too. You see, or for function f, there is a set E. For function g, there is another set, E prime. I mean, E and E prime, have no relation between them. It's not a fixed set E which works for all functions f. But still, this observation helps. In other words, you can think of this phenomenon as this. This is the set omega. This is the set omega, which is really huge, uncountable. What are the elements of L2 of omega? Well, there is a countable set here, which is the support of the function f. And there is another countable set here, which is the support of the function g. This means that the function f lives on the yellow part, and on all other parts is equal to 0. The same is for the function g. Of course, it can be some intersection. For example, function h can live on this neighborhood. But imagine how many supports, support here means a countable set, you can have in a set which is not countable. So the support changes, and we have different functions, and in each case, we can change our summation to a countable summation here, but we need to be careful that the set E changes when our function changes too. So that's the definition of this sum here, if you were not familiar with. Knowing this,
Excuse me.
is there a question?
So this set E, this can be taken to be all the values where the function is non-zero.
I apologize. Your line is. I mean, I think your connection there is a problem. I do not hear you well. Maybe.
Okay,
Maybe you can type in the chat so that I see your question. I apologize for not hearing well. So knowing that elements of L2 omega are defined this way, now we can say that assume let f and g be N2 of omega, then define the inner product of f and g in L2 of omega by, again, the sum f of x, g of x bar, x in omega. True. Let me see, what is the question? Exactly. F is the set of element x. Sushil says that we can take E to be the set of all x such that f of x is not equal to 0. True. But why this set is countable? That's the point. So I write what Sushil suggested, which is absolutely true. I here said that there is. He suggests to write, I add it here, E is the set of x in omega such that f of x is not equal to 0. That's perfectly true. The main point is that this is countable. Thank you for your comment. Now we are coming here. The inner product of fg, you multiply f of x by g of x bar, and then you sum. And our problem here is twofolded here indeed. You remember in the previous case when we had something positive, like here, we didn't care what happens at the end of the day. We consider finite sets and take the supremum. Probably what we obtain at the end is equal to plus infinity. So it's something between 0 and plus infinity. By this assumption, we exclude plus infinity. That's good. What about here? We have a sum. Omega is uncountable, and f of x, g of x bar is either a real or complex number. If we are in the real case, it can be plus minus And in the complex case, it's even worse. It can be any complex number. And if we take into consideration the comment which I gave here, you can say at the first step, there is a set E for F, and there is another set, I mean, E1, E2, set E2 for G. Both of them are countable. We consider the union, which is countable. That's good. At the complement of E1 union E2, F times G is equal to 0 because at least one of them is 0. So we studied the sum on the union of E1 and E2. Well, that's a good observation, but still it doesn't help. You remember there is a theorem in analysis 1. Sometimes we have enough time and cover that theorem. If you have a series of real numbers, which are alternating positive and negative, the order that we do the summation is important. It's a very delicate theorem. When everything is positive, the order is not important. But when we have plus minus stuff, even worse, when we have complex stuff, the order we add is really important. Again, more explicitly, when everything is positive, if you add x1 up to x2 up to x3 and go ahead, you obtain a sum. Next step, you add x1 to x5, and then come back, you add x2. Then go ahead, add x10. And I mean, back and forth in a very hazard way, you add them up. At the end of the day, you reach to the same sum. Case everything positive. If you have plus and minus elements, and the sum of the positive part is infinity, the sum of negative part is minus infinity, the way you add them up is very, very essential. You can basically construct any real number with them. I mean, with a specific ordering, you can create a series which converges to any number you wish. Therefore, even though here we had an observation that instead of omega, we can replace omega by E1 union E2, that's halfway through. It does not completely solve the problem. How do we add them up? The ordering is important. And there is no way to see here, based on the observation we have done by now, which ordering is the best ordering. But the good thing here is that we can show, and that is our next exercise, that the ordering is not really important. The second exercise, to show that this definition is a good definition, show that the sum put absolute value is finite. Of course, with this assumption, do not forget our assumption. With this assumption, the sum of the positive objects, I mean, you put absolute value, is finite. And when this is the case, the ordering is not important and the summation is well defined. So everything is in good shape. And thus, the sum of f of x, g of x bar is well defined. Up to here, it covers the definition of inner product in L2. To continue, it's 15. I usually, I mean, in these courses, which are 3 hours in a row, the tradition at Laval is that we give 50 minutes and then 10 minutes of break.